I want to do one more example of I want to do one more example of the method of characteristics, and I think that I mean, as we go along, we've not just solved some problems and understood the computational technique, but we've always been trying to extract more information, because our goal is not just to solve this problem, but to solve all problems of this sort. So we've always been kind of, like looking ahead, and I think that if we solve, I think that if we solve one more problem, we will be in a very good position to, discuss a more general existence result. Okay, so this is good old Berger's equation. I'm using the notation x1 and x2 just so that it is consistent with the notation that we've used, in the development of this material. But this is just Berger's equation. We're going to solve in the right-hand half. I'm thinking of x1 as my temporal variable. So in the notation that we used when we solved this problem by other techniques, this was our t, du dt. So this is my temporal direction, this is my spatial direction. So we're going to solve for positive values of time, and there will be an initial value, specified at t equals 0. You're solving you solve the equation in the open set, and then you have this initial value prescribed on the boundary. Okay. So anyway, as I said, I made the notation consistent with what we've done throughout. But this is just Berger's equation. You start the method the same way as before. You identify what is the f of your problem. This is your newly independent variable p1, z, and p2. So my function is p1 plus z, p2. You want to choose curves. The goal is to choose curves that start on the boundary and go into the region, right? And remember the development of the material. We want to choose the curve gamma in such a way that its velocity vector, the velocity vector, coincides with df dp. So go back to your equation, df dp1 is 1, df dp2 is z. Okay, so in coordinates, this is that's the vector form. Component-wise, you'll have, this will be x1 and it will be a function of s, and x2 and it will be a function of s. The velocity vector is just calculated component-wise, and so you want, if you write this out component-wise, you want dx1 ds equals 1, right, and dx2 ds equals z. This one I can solve right away. I integrate and get s plus a constant. You want your curve, you want to parameterize it in such a way that when the parameter is equal to 0, that you're here on the boundary, where our initial value will be prescribed. In order that happen, you choose A to be 0. All right? This is a quasi-linear equation. This is a quasi-linear equation where the coefficient of my highest order term depends on u and derivatives of strictly lower order. And so I can't solve this one alone. I've got to go on to the z. I've got to go on to the z system. Okay, remember where you get your z system. That's from these other terms out here, which in our case are 0. All right? which in our case are 0. And so dz/ds is 0. That means that z is a constant. Put that back in to your equation for x2. Integrate quickly and you solve. x2 is equal to that constant times s plus another constant. And now I'm able to write down the parameterized curve. Okay, it's looking pretty good so far. It's looking pretty good. In this equation, there's no need to go on. You don't have to solve those p equations. And so we're ready to go on to the step where we incorporate, oh, I'm making this thing jiggle, where we incorporate our initial value and then try to recover a, well, z is u, right? So what is, but it's not, well, let me say it like this. You're not saying, I mean, where did z come from? Z is equal to u gamma of s. You're not saying that u is constant. It's that u, when evaluated along this curve, is constant. But of course, it's not just one curve. It's a family of curves. It's constant along each one. Okay. And so that's what we're going to try to do now, is recover u as a function of x1 and x2. Okay, great. So let's see if we can take the final steps and express u as a, finally at the end of the day, as a function of x1 and x2. Because you want to be able to say what is the value. You're solving a PDE in this open set. You want to be able to say what is u at this point. Okay, so this is where we had gotten before. We solve for the curve. These are both constants. They came, think of where they came from. They came from constants of integration. So let's solve for c. If z, remember that z, we solve for z. The differential equation for z was dz/ds equals 0, so z is a constant. So in particular, at 0, z is equal to that constant c. Now we do this all the time in math, right? We do this all the time in math. We calculate the same thing two different ways, and then we equate our answers. This is from before. Now from my formula, z at 0, what is z? What is z of s? It's u evaluated at the point gamma of s. So at 0, gamma of 0 is equal to 0b. So at s equals 0, z of 0 is equal to u at that point. And then I guess I didn't say this before. This is my initial value. Let me abbreviate it that way. The initial value was specified, although I forgot to specify it. Remember in the original problem, it said the values of u were specified on this boundary. Okay, so you can view g as a function of just one variable. You can say it either way. You say g of 0b or just g of b, because this is a one. I kind of prefer it this way because it is a one-dimensional set. So g is a function of the height, but this is given in the original problem. Okay, equate them. Then we solve as c. We solve and we see that c is equal to g of b. So I put that back. I substitute that into my. I substitute that into my equation, my vector value equation for the parameterized curve gamma. Okay, b was also a constant of integration. But we're not going to solve for that because remember, I don't want to muddy the waters too much, but you could have really, if you wanted, you could have, for every choice of integration constant, you get a different answer. And that makes sense geometrically because you've got really a family of curves, not just one curve, but a family of curves. And if you wanted to, you could, write a little subscript b to denote the unique curve that starts here. Okay? This is a very simple curve, right? This is x1, and so you can easily, just eliminate the parameter, and the form that you have is m x1 plus b, right? Slope. Here's x2. So x2 is equal to g of b times x1 plus b. That's a line of slope g of b that intersects the vertical axis here at height b. Okay? And along that, well, let me sketch it in. So whatever g is at this point, that's the slope of this curve. And then u, the solution u is constant along it. Whatever the initial value is here, the solution u is constant along this curve. So if you want to express u as a function of x1 and x2, right, then you've got to determine for a given x1 and x2, what is the unique line? What is the line? I shouldn't say unique. In fact, these calculations are really easy. All right, the examples we did previously were not that hard. I mean, you kind of suspected that they were invented to work out, not to be not too difficult. And this one's even easier. But, you're going to see, maybe you're already seeing. Maybe you're already perceiving some difficulties shaping up. Because you see, G is not constant. Each one of these, you get really a family of curves. And each one of them might have a different slope, right? Each one of them might have a different slope. And so, if you wanted to express u as a function of x1 and x2, first you have to determine which line does it lie on, and where does that line, the value of u here will be whatever it is, whatever g is here, right? Because we just said a moment ago that the value of u is constant on those curves. But because the slope isn't constant, because those slopes can vary, you don't know whether x1 and x2 actually lies on only one curve. And if it lies on more than one curve, remember that the value of u is constant along these lines. Its constant value is equal to whatever the prescribed initial value was here. Is there any guarantee? That those constants are equal? U is constant along this line, and u is constant along this line, but possibly equal to different constants. And then you will not be able to say what u, is at that point. Okay, so let's look into that a little bit. Here's another way to say it. Compare it to compared to the problems that we solved previously, you had to determine which line to find u as a function. To find u as a function of x1 and x2, you had to determine which of you had this family of curves, which hopefully sweep out the region. And you had to determine which of those curves the point x1, x2 lay on, and at which parameter value it was reached. So here you've got to solve for b, right, because that's this point. And for s, the parameter value at which x1 and x2 is reached. Okay, so let's look at that a little bit. I mean, that is like to formulate the problem, and then let's see what we can do with that problem. We're trying to express u as a function of x1 and x2, and so what you've got to do is you've got to determine, well, you've got to determine two things. Which is the unique, is you've got this family of curves, and you've got to determine which is the curve that x1 and x2 lies on, and at what point that curve intersects the boundary. And then whatever the value of the prescribed boundary value is there, u is constant along the curve, and so that will be the value of u at x1 and x2. Okay, so you're trying to solve. This is what we had before, right? You're trying to solve for both s and b, right? Remember, b is that like you could say that's the y-intercept. You need to know where you intersect the boundary, and at what parameter value you reach this point. And, maybe here I really should, for emphasis, write gamma lower b, because it is a family of curves. Which curve does it lie on, and at which point, what parameter value is it reached? And so you got to solve. You're solving for s and for b, and if you understand this picture, you can see that the success is not, it was by no means guaranteed, right? Because first of all, we already saw you could lie on more than one curve. Also, well, it doesn't happen here, but of course, now you got to, start thinking about all the worst case, all the nightmare scenarios. Does this curve even intersect the boundary at all? Okay. So when you're saying, I have to solve for s and b, you can't say that you can always, even theoretically, it might not be possible to solve for s and b, let alone, can you literally solve for it? So you got a function. So let's conceptualize it this way. Let's think about this more generally. Basically, what is the issue here? Before what is the issue here? You've got a function of two variables. If this was little gamma, I'm going to call this big gamma. It is a function of the variables s and b, and I'm trying for a given x1, x2, for a given choice of x1 and x2, I'm trying to solve gamma of s and b equals x1, x2. I'm trying to solve for s and b. Okay, so look at your inverse function theorem. Let's look at the matrix of partial derivatives. D gamma ds, that goes down my first column. The derivative of this, I wrote def here, because this defines. I am defining this new function gamma. D gamma ds. The first component, the derivative with respect to s is 1. The second, here in the second component, the derivative with respect to s is g of b. Okay, my b derivatives. In the first component, the derivative with respect to b is 0. And in the second component, the derivative with respect to b is g prime of b, if g is c1. or not, if g has a derivative at all, okay, times s plus 1. Is this thing invertible? We want to apply the inverse function theorem. So let's take the determinant. This is what you get. It's very interesting because what you'll notice, it'll be locally invertible. It'll be locally invertible near, say, g, near, for example, that point 0b. Notice that having g constant is favorable, right? Because if g is a constant, then the derivative of g will be 0, and then my determinant would always be equal to 1. Think about the picture. G of b being constant means that those slopes, the slopes of those lines are all equal. And so no matter what point, x1 and x2, you give me, right? It lies on a unique line, and u is constant along that line. Okay? Okay, but you see, if by the way, S is our, you can think of other scenarios. S is our temporal variable, right? And so time variable. And so we're thinking of S as being bigger than or equal to 0, strictly bigger than 0. I mean, the way we parameterize it, is that if S is positive, then x1 is positive, and so you're going into into the right-hand half of the plane. Okay, and think that. So here's another favorable scenario. What if g? I mean, just algebraically, you can see that because s is positive, if g were an increasing function, then that would also guarantee that my determinant never be 0. Think about the picture there. Then you have, the increasing slopes, but still those lines don't intersect, and so that's another favorable scenario. You see it algebraically, analytically by the calculation, and you see it in the picture too. G being an increasing function, that's also a favorable scenario. You'll be able to solve. Given any choice of x1 and x2, you'll be able to solve for the unique b and the unique parameter value, and then you'll be able to say, here's what u is. Here's the value of u at x1 and x2. Okay, g. Of course, g could be more complicated than that, and then if you've got slopes, that are, sometimes positive, sometimes negative, and then you can get intersecting lines, and if the initial value here does not agree with the initial value here, then you'll have u is equal to 1 constant along this line, u is equal to another constant along this line, and therefore your solution cannot exist for values of time bigger than that intersection point. Okay, so I think you can, as I said, this example started off so easy. The calculations were going even better than in those previous examples that seemed even a little bit artificial. This is a real life equation. It's so simple, but it really illustrates a lot of the issues that can arise. So when you think about, now let's think carefully about, let's just think back to the examples that we have solved by this method. And let's start to sort of catalog some of the issues that arose, some of the things that could go wrong. And, so these are points that would need to be addressed if we were to try to formulate, some more general existence result. Let me add a little postscript to the example that we just studied. I said this really quickly. Let me explain a little more what I mean. If G has to have a derivative for you even to be able to write down that formula, because it contains a G prime, right? But let's say it's better than that. It's that G is C1. Remember that to be in the class C1. Let me remind you the notation. To be in C1 means not only that you possess a first derivative, but that it be continuous. So let's say that G1 that is the case. Well, that's not that would maybe use alpha and beta. Let's say you are only interested in some compact interval and that G were C1. Well, then there would be a single value of T. There would be a single value of T for which, solutions existed for all values. Here's what I mean. This slope might be such that, at some point, these two lines intersect, right? But if G is C1 and the interval in the vertical axis is compact, then these slopes cannot vary too quickly, right? And so then these slopes can't vary too quickly, and so there will be a single time interval. You'll get local existence because there'll be a single time interval that works for all of them. In other words, that none of these, if the time parameter is strictly less than this, none of those curves intersect. And then each point in the region will lie on a single curve that touches the boundary once. And then you'll be able to write down, what is, at the end of the day, U at that point. Okay, now that's related to our little catalog. Let's start to, think of the examples we studied, and let's start to enumerate the problems that might arise, which conveniently did not in the early examples. The first thing, let's make this number 1 on our list. We did even a quasi-linear, we did a linear, semi-linear, and quasi-linear example. In the fully nonlinear case, all 2n plus 1 equations will have to be solved. The other thing was, so that's the first thing, that in the more nonlinear it is, the more equations you have to solve up to the fully nonlinear case where you need to solve all 2n plus 1 equations. Okay. Now think back to some of the examples we calculated. We see that there are restrictions. There are restrictions on the set along which either boundary values or initial values can be specified. So let's make that number 2. There are restrictions. There are restrictions on the set along which boundary or initial values can be prescribed. This example that we just solved, that's a perfect example. You've got this, you've got an initial value, and well, wait a minute. We did solve one where they were literally straight lines. Straight lines of the same slope. Okay? Even in the example we just solved, so that'd be one example. That one worked out just fine. Berger's equation that we solved just now is still fine. It's still fine. The problem maybe here is this. It's not that there's something wrong with that choice of set. Okay. Now we had another example. So yes, specify. Yes, you can specify boundary or initial values on this set. How about that one where, do you remember where we're solving in the this quadrant of the plane, and we had these portions of circles? If you try to specify this is from the earlier example, if you try to specify initial values on one of those curves, do you remember this? That I'm thinking about that example where the region in which we were solving was swept out by those quarter circles. What would happen if you, and we had, if I remember it correctly, we had boundary values specified here. So each one of those curves, each one of those curves intersected the boundary once. And each point in the region lay on precisely one, not more than one, but precisely one curve. What would happen if you tried to specify, instead of specifying initial boundary values here, what would happen if you tried to specify boundary values here? This wouldn't work, right? Because you remember that the restriction of u to this curve satisfies an ODE, all right? And that ODE, it's first order. It is first order. So its value at every point on the curve is uniquely determined by this boundary point, by just that one, its value at just that one point. So if you're trying to specify boundary values here and here and here, not all choices will work, right? Because once you've given it here, the values at these subsequent points are all determined. So you can't specify arbitrary. You can't specify arbitrary whatever boundary values you want along that curve. You could, in principle, specify if they all satisfied that ODE. You could specify that, but then you've got a different problem, which is that other points in the region are not reached. They are not reached by curves. They are not reached by curves that intersect this set where you want to give your boundary value. So you cannot specify. So that's not a good choice where if you want to specify your boundary value. There are restrictions. There are restrictions on the sets along which you can specify boundary or initial values. What I mean is, let me just draw the picture one more time. Like say, we were solving, when we did this problem, we were solving in this open quadrant of the plane, and boundary values were given on this portion. Let's say you wanted to solve in this region, this open region of the plane. Whoops. Right, and you want to specify boundary values here. But for the same equation, that won't work. That will not work. Okay, there are restrictions. There are restrictions on the set along which you can prescribe boundary or initial values. What is the optimal case? What is the ideal case? You want the region to be swept out. You want to be completely swept out In other words, the region is the union of these curves. You want it swept out by these curves, each of which touches the boundary exactly once. Okay. What else? What else? The example we just did, Berger's equation, was so simple, but it illustrated an important point, which is that you might not be able to solve explicitly for x1 and for u as a function of x1 and x2. Sometimes you need to invoke the implicit, or, excuse me, I've got something in my eye. Sometimes you might have to invoke the implicit or inverse function theorem to prove existence of it. You know, you might not be able to like write it down easily by hand. You might need to invoke the implicit or inverse function theorem in order to prove existence. But again, you know, it's not the end of the world, because look, okay, first of all, you could have two different, you know, there are two possible goals there. If you want to prove existence, then you have done so. Say you want to, you know, maybe you're doing some kind of numerical work or some application, and it might be good enough to get an approximation. Look in the, not just the result, but to look into the details of how the inverse and implicit function theorems are proven. You'll see that it is an iteration. It's a fixed point argument. It's an iteration scheme, and by controlling your errors, which you know isn't such a big deal, you can easily use those to approximate solutions as accurately as you wish. Now there's another thing. Well, I forgot, I haven't been. Okay, let's make that number 3. Number 3, you might not be able to solve explicitly. You might need to invoke the inverse and implicit function theorems to prove existence, to solve for x1 and x2 in terms of the parameter value or x1 through xn, whatever, in terms of the boundary, the point on the boundary, and the parameter value. Okay, look, now there's a fourth one. I mentioned a moment ago that when you, if you're dealing with a fully nonlinear case, then you really do need to solve all 2n+1 equations. You have to solve the equations for the ODEs for the P1 through Pn. But remember, they aren't just equations. They are initial value problems. They are initial value problems. In the equations for the xi's, right? You have an initial value if you want to touch the boundary. The z you're given boundary or initial values. What about the p's though? Remember, these are you have to solve not just differential equations but initial value problems. And what we're going to see in a minute. So that's the fourth issue. When you get into the fully nonlinear case, among most of those initial value problems, finding the correct initial value for most of them is not a problem. There's one that is a problem. It's not just a question of computational difficulty. I mean, it is a bigger system. It's a bigger system. It's going to be harder. But again, it's not just a question of computational difficulty or a bigger system. There is a genuine problem there. That genuine problem deserves more careful explication, and we will dedicate a separate discussion to that.